Right. Looks like the stream is working. See myself. All right, let's see. Appears to be 24 concurrent viewers. Not starting yet, but just to make sure that everything's working tech-wise, can somebody post a quick message on the chat? And I'm here. Nice, thank you, Henry. Appreciate that. All right, cool. All right, if you stick around, I assume most of you are effectively done with the project, or if you're taking a break for the lecture from the project, that's a good thing as well. We'll be starting in a couple minutes. Stick around. Be right back. Yes, good morning, I guess. I know it's noon, but I don't know what that feels like. And a quick note before we get started. Anybody from the staff that might be on the chat? I wonder if you can post a quick message just to see you're there. And we'll be starting in, let's say, give it a minute or two. Yes, that's a good question. How is everyone? Hope you're all doing some self-care. Um, so my kids started school, and that's definitely a big theme, which I find is actually quite important. Whole concept of self-care in these times. All right, so rounding maybe another minute, and we'll officially get started. All right, let's just get started. Hello, everyone. We have around 115 people. I think that's good. My name is Hector Garcia. So yes, I'm not Dr. P, David. There's Dr. P. It's on the chat. Awesome. So, all right. So before I get started, some of you might have missed my intro a few weeks ago when we started the semester. I got my PhD at U of M. I've been teaching 281 for a few years, amongst other courses. I'm a developer manager at a company called Criteo, which is an advertising technology company, formerly known as Hook Logic. It was a startup in the Ann Arbor area that got bought by this French company that's called Criteo. We're on Main Street in Madison. So I have a lot of fun there doing machine learning, engineering, and development. But I also enjoy teaching, specifically this course. And I'll talk a little bit of that throughout this lecture, actually, which is titled The Standard Template Library, the STL. This is in C++ what we use as pretty big standard. Kind of started in the early 2000s. Well, it was always there, but it got really formal around the early 2000s, believe it or not, as they started developing a lot more versions of it. So we'll talk a little bit about that as well. And some of you might be wondering, like, well, this would have been good to know kind of before the project one, which is due today, but there's only so many topics that we can cover before the project is due. So this actually covers a lot of the STL, some of the stuff that you might have learned throughout working with Project 1. And then we'll also talk about additional things that you have to keep in mind for the rest of the semester. So a couple of things we might be, this is my basement. We're just as likely to be interrupted by 3 boys or 2 cats. That's why I'm doing my lecture standing, trying to avoid my cats jumping on the table. All right, so, and then I'll basically refrain from looking at the chat as much as possible. Usually I try to make my lectures really, really interactive with a lot of Q&A, and I stop for questions every 2 or 3 slides even. But of course, that doesn't provide for a good lecture in this type of stream situation. So I'll try to address some questions on the chat, but if I don't get to your questions, it's because we're just trying to move along. And please make sure to visit our lecture Q&A. It's specifically for questions that we cannot get to during this live lecture, and of course, general profits hours. All right, so let's just get started. We have a couple of slides here on Project 2 that I will skip because we haven't assigned Project 2 yet. I will basically come back to these Thursday's lecture when we do assign project 2. But if you want to start reading about it, feel free. So that's why I kept them in the slides here. But again, we'll cover these on Thursday, these 2 slides about project 2, because you might be wondering, like, why are we talking about project 2? We're not still done with project 1. In this course, we do start with projects early. So that's why we're already talking about project 2. More on that Thursday's lecture. All right, so why C++? Like, why do we teach this course in C++? For that matter, why do we teach most of UMM's computer programming related courses in C++? You probably already heard some answer to this, and I can tell you from experience, in hiring and recruiting engineers, folks that learn the fundamentals, such as what we teach in this course in C++, have a better time adapting to other languages. And then within C++, it's particularly important to know the STL, which is Standard Template Library. And there's a quote there from, like, I think Quora, top coder. And so if you master the STL, you're mastering C++, right? And so and then by mastering C++, that allow you to master other languages easier. Like, I've had experiences where C++ developers that know the standard template library in a matter of days will learn other languages quite easy. Might not happen if the fundamentals that they learn were not in C++. So what is the STL? Stands for Standard Template Library. The fact that it's template is particularly important. That might be different from other standard libraries in other languages, which might not be templated library. It is part of C++, and it was kind of always there, but it really kind of started to be formalized and expanded upon with C++ 11, which, the 11 stands for 2011, although it started a bit sooner than that. But basically, one of the seminal versions of C++ is C++ 11. Of course, by now we're like at C++ 17, now that all these versions have been standardized. That is part of standard library C++, so stdlib-c. It is fairly well documented, and we'll talk about a few resources there that if you haven't found yet, we'll point them out to you. I'll speak to my favorites at least. It is pretty high quality, so a lot of people have contributed to the development of the STL, so it's highly optimized. And then all implementations are entirely in headers, which you might be wondering, why is that? And that is because, it facilitates linking. So even though you might have learned in other courses that maybe your headers shouldn't really contain the implementation of code, now we're kind of sometimes we'll tell you otherwise. Like in the STL, actually a lot of actual implementations are included in the header files. Okay. So some of the contents of STL, and there's a link there to a Wikipedia article on the STL, because if it's on Wikipedia, it must be true. But for the most part in this course, you'll be paying attention to containers and iterators, memory allocators. It also contains a lot of utility and function objects, or functors, if you recall from 280. But it also contains plenty of algorithms to use, right? And in fact, some of those are related to sorting, which after this lecture, we're basically going to go into the topic of, first we're going to cover heaps, which involves a sorting topic, which is heap sort, and then we'll go full on discussing a lot of sorting algorithms, so all sorts of sorts we're going to be talking about. Okay, this is an important topic in computer science. All All right, so some of the resources that I mentioned I would talk about, they're listed here. I know my particular flavor is CPP reference, which actually has this run this code feature, which is pretty interesting, although sometimes doesn't work. As far as I can tell, when I go in there and try to run it, sometimes it just doesn't work. But I think most of the time it does work. C++.com is also particularly useful. I kind of basically go back and forth between these two. And then the reference books that we use in this course are also particularly interesting, but of course they're books, and who needs books these days? It's just everything's online. But no, they're particularly useful to have if you can find some PDF version. But really, day to day, what I use most is basically either of these two websites for Consultant the STL. Okay. So the STL is a library, much like any language has its own standard library. And then, so in general, you want to ask yourself, like, at what point do I use a library versus I implement some functionality or algorithm by myself? And that is, basically a gray area. You kind of, as you develop more and more, you're going to develop a better eye for what you should basically rely on the STL for versus implementing your own. And of course, sometimes you won't have an option. Sometimes you're trying to implement an algorithm or functionality where just STL does not provide anything close to what you're trying to implement. So you're going to have to do it yourself. But in those are gray areas. It's very important to know the capabilities in the STL and what you can get from it. So that's why we study it here. So some of the pros to this, of basically trying to use a library rather than do it yourself, is that it's done for you, right? You don't have to spend the time implementing it yourself, testing it, debugging it. Basically, all that work would have been done by somebody else, and then you basically just use the algorithm. So things like intro sort, which you probably are not familiar with right now, but we will discuss in a later lecture, which is, we won't discuss it in that much detail. But it's basically, intro stands for introspective. So basically the sorting algorithm kind of decides which sorting algorithm to use that best fits the particular input. Red-black trees, which we do not discuss in this course, but we do discuss something that's quite similar, which is AVL trees later in the semester. But if you read about red-black trees, they're particularly useful. And then some things are particularly hard to implement, and you don't want to spend the time to implement yourself. Hash tables, for example, although oftentimes hash tables do require kind of particularities if you want to make it highly optimized, and you oftentimes, specifically for hash tables, you might not be able to rely on STL. But things like merge sort, that's which in the STL is called stable sort, that's something you can straight up pick up from the STL library. Then you have utility algorithms like max, basically getting max from, I believe it's 2 arguments to that function. Then swap, basically swapping the values. Again, these are not particularly complicated functions to implement, but definitely having some uniformity in how these functions are used throughout your code, because all they're doing is, calling the STL is nice, right? Of course, relying on the STL reduces debugging because it's code that you can assume that it's fairly well implemented and tested. And so it reduces your time in debugging because oftentimes this is where we spend a largest portion of our time as developers, okay? Enough so that at companies, you do have positions where it's a QA, quality assurance folks who are dedicated to testing code, right? Because it's so much work to do. So not just implementation, but testing is particularly important. All right, and say some of the cons is, you know, a lot of these implementations are by definition generic, right? Because they're trying to kind of be a one-size-fits-all kind of approach. Because when, like, imagine if you were developing your own library and you develop some algorithm, you would, and you're intending it for other people to use, then you want to implement it in a generic fashion so it can cover as many potential, call it input cases, or you know, particular contexts in which you intend your algorithm to be used. And so in trying to do that, you know, it might not be the most implemented in the most optimal way, because there's definitely this balance between generics and optimization. And so if you're trying to develop general purpose implementations, then you're going to get hit in terms of optimality. Okay? So specialized code may run faster. In fact, oftentimes it does, even if it's by a small amount. And that's because if it's specialized code and you know the context in which the algorithm is running, then you can, you know, you might be able to skip unnecessary checks on input, right? You might, based on assumptions on the input, your algorithm may do a lot less steps to arrive at a solution. And actually, we're going to see examples of this when we cover sorting, not next lecture, but the lecture after, where for the sorting problem, we kind of make assumptions about when the sorting is, or what the sorting algorithm is about to sort, and therefore we can optimize part of the code. Okay? So in order to determine the trade-offs between these pros and cons, it's particularly important to understand the STL capabilities in depth, which is what we're trying to cover here. And some of the algorithms that it covers, right? So it's the sorting algorithm, which is implemented in n log n worst case time. In fact, sometimes it's faster, right, than that. Largely because behind the scenes it's actually this intro sort algorithm that I mentioned earlier. So it is a bit adaptive, and so in that sense, it can run quite fast, right? But of course, it's not an asymptotic. It's never an asymptotic improvement. So asymptotically, all that we can say is that it's an n log n algorithm. There's the nth element implemented in average case linear time, which is quite interesting. Nth largest element or smallest element in a sequence. So it's important to understand all the details about this library, and also the versions that you might be using, because if you're, you know, for example, in older versions of libraries, you might get behavior that you don't expect, given that you might have been working with a later version of the library. So for example, older STL, linked lists did not store their size, right? So if you write code that's, say, based on C++ 17, where you do have the size, then that code might not compile using an older version of the STL. So those are all the things that you have to watch out for as you sort of keep in mind the STL and what it covers. So there are plenty of STL algorithms available. C++.com is particularly good for looking at these algorithms. You can basically pick up examples from there, you know, compile them, run them. I know I sometimes find useful online GDB. I'll type it in the Slack channel. I don't know if folks know about this online. In fact, I might use it I don't know if it's .com, I don't remember, but if you search Google online GDB, it's basically exactly that. It's GDB online, and you can copy paste code and then run it real fast. You can actually change the version of the STL that you would want to compile with. So we encourage you to basically read up all of this. We also, and probably Dr. P talked about this when he was going over his lectures earlier in the semester, we do have an STL and U resource on Canvas. Make sure to read that up. Hopefully you have already because of Project 1, but make sure to revisit it. See if you can pick up something that you didn't before, but then also consult all these resources that we're giving you. Okay. So, you know, it is particularly important to keep these resources in mind because you're never going to remember everything that is in the library at all times. And also it's almost, it is impossible, I think, for one person to just keep track of all the changes as the STL versions keep going. So find a good, say, MO for consulting these references to understand the STL, right? Skim through documentation, study what seems interesting. Always useful to copy, paste, and run the code. Day to day, I consult standard libraries basically on a daily basis as I develop my own code. So particularly useful skill to develop. So some of the things that you would want to pay attention to as you look at the STL with regards to this course is as it relies on some particular C++ features, which I'll go over some of these in the next couple of slides. So it uses type bool. You should be quite familiar with that. But what you might not be quite familiar with is const correctness and const casts. That is something that STL does rely on, basically, that if some function in the STL takes as input a non-const parameter, then it's, you need to stick to that. So you could not pass it a const argument to that function. That's what we mean by const correctness. And of course, these are all detectable at compile time. Namespaces, should be quite familiar with those, as well as templates, inline functions, exception handling. That is, some of you might have seen it. In fact, if you didn't know the difference between using the square brackets in an array, so something like, oops. Oh, trying to get my pen to work. One second. It was working a minute ago. Maybe I just need to stick it in here. There we go. All right, so if we have an array that's supposed to be an A, let me erase it. Oh, that's not what I meant to do. All right, there's my array. The difference between doing this and this, okay, in a vector, is that the first one does not have any sort of exception handling on the range of the index that are acceptable to that vector, right? Whereas the second one does. And I don't know, my pen went away again, not working. All right, but this. So that's what we mean by exception handling. So yeah, vectors do have some functions that include exception handling, like for example the .at again, checks for the range or that the I value is within the acceptable range given the size of vector A. Implicit initialization, that is, if you've ever covered implicit casting, basically very related. We'll talk about that in a little bit. Operator overloading, which you'll get to know quite a bit of in Project 2. If you haven't used it yet, you might have, depending on how you implemented Project 1, you might have used some operator overloading, which is exactly that. It is taking an operator. In fact, it could be the square brackets that we have there that I wrote up there on the slide. You could overload the square brackets operator on a container. Not recommended that you do so, but you could. And so the same deal, you can overload the assignment operator. You basically, in C++, which is different from other languages, in C++ you can overload any operator, as far as I remember. Can't think of anything that's excluded. It includes extended syntax for the new operation, the allocation of memory. If you want to stick with the standard syntax, that's completely fine. But I'll let you look up that extended syntax because I honestly don't remember it. And then keywords explicit and mutable. Those we're going to talk about because they might come up in Project 2, or actually they will, I think, in Project 2. They're not, they sound complicated, but they're not. So we'll talk about those. Actually, I think in the next slide. So on the keyword explicit, basically what that means is that you're preventing the compiler from doing any sort of implicit on that line of code or on that object, depending on the use of the keyword, right? So for example, if you have explicit feet inches on the constructor int feet, right? This one right there. Oh, my pen stuck. Let's see if I can get it. See if it works now. And there it is. All right, so this right here, explicit feet inches int feet, it basically will disallow conversion when calling a function that expects a feet inches object. Okay, so this would be okay, right? But then this will cause an error, right? You can think of this similar to if you had, I think my pen ran out of battery, and that's why. So let's stick it up here. Sorry. All right, so I don't have a pen, which is sad because I was looking forward to using that throughout the lecture. I basically have it charging now. So on with explicit. So the idea is that it in the one that says that's an error, basically that means that if you did not declare the feet inches object to be explicit, it would try to implicit cast the value 3 into a feet inches object because you would have declared some constructor that takes on an integer. Because that's available, then C++ would implicitly try to do that. But most often you don't want C++ to make that decision, so you declare it explicit so that anyone that tries to call the constructor that has an int parameter will have to do so with the line that's okay, right? Which is the normal way for calling the constructor. So that's basically what explicit does. Mutable is more interesting. A mutable member variable can be modified by a const member function. So basically, in general, mutable is kind of a way around const. It's kind of like the anti-const, which for most situation, it would be bad to use, right? Whenever you can, I would say you would want to avoid using, at least this is my opinion, you would want to avoid using mutable. But there are situations in which it's quite useful, right? One example would be that you're dealing with a reference to an object, and maybe that reference is const, but you still might want to modify one of the member variables inside of that object. So if that member variable was not mutable, you would not be able to change it, right? Given that the reference object itself is const. Okay. But if it was mutable, then you could. Okay. So look up examples of those. I was looking forward to typing one with my pen, but alas, my apologies. I should have recharged it before lecture. Okay. So a big benefit of the STL is that it does not rely on pointers, or more precisely, it does not rely on explicit pointers, because it does rely a lot on iterators, which are basically behind the scenes, they're pointers. And so that's good. And some of you might be thinking, well, I thought, you're only, a good C++ developer if you know pointers and, they look fancy and they, but really, in general, all languages have tried to stay away from using pointers because, well, they're very error prone. So it's very easy to make a mistake when you're just dealing with pointers. There's, no real need for using pointers. Okay, maybe there's some particular situations in which they are quite useful to have, but those are largely minimal. I mean, every language that came after C++ have just basically tried to stay away from pointers, right? So Java, Scala, Python, right? There's no pointers at all. Okay. So here's an example on the slide that is using pointers. I believe this code would, is this the one that reverses? I think so. It just reverses the C string. That code, very hard to tell what it's doing, and what is happening at each step of the simple algorithm. And it's very, type unsafe, if you will, right? Whereas if your code were not relying on pointers, it's, a lot more type safe, because you would explicitly have to define what type your algorithm is working with, or your function is working with. Okay. Let me pause here for, I think we're doing good on time, so maybe I can see if there are any particular questions so far. Oh, I see that we have Blake in there, so it's great taking care of questions. I know Dr. P was on there before. I wonder if in the future pointers will go the way of goto. Curiosity useful? Yes, I think it's already there. Underrated one. I think that's basically what pointers are looked at. That's how we look at pointers right now, right? It probably, you can produce really fancy code. And I will say sometimes it's quite useful when you're developing generics, so meaning algorithms that should be able to work with a lot of general implementations. But for the most part, given that most code is not really implemented in a generic fashion, right? And so if you go on a career as a developer, you're going to be developing code for your organization or company or whatever it is, and it's going to be your own code, right? More than likely, you're going to be in that boat than in going to some other company that might be putting out libraries, and you have to think about how your algorithm is used, and therefore account for generic situations in which your code might be used. So more than likely you won't be in that second boat, but so that's why most code kind of falls into like, let's just avoid pointers, let's just implement it how we need it to be. Most STL implementations have the best possible big O complexities. This is by way of, oh, I saw a question. Mutable means I can still change certain member variables even if the object is const. Yep, that is what mutable would be. Like if you make that member variable mutable, I feel that's basically the only real reason why you would want to use mutable, because mutable, the keyword, you can actually use to get around const for the most part, right? So if some variable or object is declared const, and then you basically pass it to a mutable, then it kind of, I'm really trying to think whether that is possible, but I think the most useful situation in which you could use mutable, and I think for me, I would try to stay away from it unless it's the scenario, is the mutable data member can be modified even if the object reference is const. Okay. All right. So, for example, sorting in STL, it would be hard pressed to think that you could beat the performance of STL sort, except only for some really specific situations. Same thing with nth element, which is in linear average case time. Now, some have poor performance even with a good implementation. Yeah, so I guess this kind of summarizes what I just said. Because people have optimized STL quite a bit, it's hard pressed to find a way to kind of beat it. Some of the STL containers that you might be kind of already familiar with, at least some of them. For example, vector, you're familiar with that from project 1. Same deal with deck. And then there is an STL stack and queue, and you might be wondering, well, why didn't we use stack and queue in project 1? Well, it's largely because in the project we wanted to have a container that would behave both as a stack or a queue, depending on the situation. So deck allows you to do that, but not the formal stack and queue in STL. In fact, in STL, those are adapters, meaning that you would have to, when you declare your stack or your queue, you don't have to because there's a default, but you should choose a container that you want STL to use behind the scenes, like either a vector or a linked list or a deck. So that's what we mean by adapters. Bit vector is the same as a vector bool. This did not used to be the case, but now it is, that they're effectively both the same thing. So all the optimizations that they had for bit vector have basically also been adapted to work on vector bool. You have set and multi-set, and then you have the unordered versions of those. So set is exactly that, basically just a container that holds some values, and you can pass a fast query to determine whether the element is contained on there or not. Multi-set is you can have multiple copies of the same value. That's what that means. Ordered versus unordered. Unordered would mean that there's basically no guarantee in the ordering of the elements that are inside of the container, right? So if you were to print all the elements in the set, the order in which it comes out one time might not be the same order in which it would come out the second time you print, after you might have done some insert or removals from there, assuming that they're supposed to have the same elements after all those changes. And so a map is very similar to a set in that, well, or more precisely, a set is very similar to a map, except that a map is really not just a single value that's contained, but it's a key value pair. So in an unordered map is effectively a hash table. Okay? And then later on in the course, we're going to go over hash tables quite a bit. But then you also have the unordered versions of those, which is what I just spoke of. A multi-map would mean that for the same key, you can have multiple values, right? Which is also often quite useful. Then you have a list, which I assume you're all familiar with. And then you also have array, which is actually not particularly useful, given that we always have the option to use a vector. Okay, so arrays are basically just like your normal traditional arrays. So it's fixed size and all that sort of stuff. It's I don't know why STL has it, because it's not particularly useful. Cool. Let's see, any questions? They're the same. A bit vector would mean a vector. Oh, that's Blake talk. Okay, yes. All right, cool. I really struggle with this kind of like not doing Q&A while doing a lecture. It's kind of weird. All right. So STL does have multiple linked list containers. You have a list, which is a doubly linked list. So that means it also keeps track of the size. So it can produce the size of the list in constant time. It has S lists, which is singly linked, but it's based on smart pointers, right? I guess that's what the S stands for in S list. Do not use an S list. I mean, I really can't think a reason why you would want to use it, but I guess you could, but don't. Okay. We will deduct points because of the use of S list in, say, the project. Then a forward list is effectively a plain good old singly links. It doesn't even keep track of the size. Okay, and so, not very useful. I've never used forward list, to be honest, but it's there. Okay, so all right. So here's some code for copying and sorting arrays. Kind of just shows off how you would use, say, the sort algorithm in STL. Okay, so let's see if my pen charged enough so that I can write some. All right, so I mean, this is code that you should be familiar with. This is the declaration of a vector and then also a plain old array. Then this basically right here inserts effectively a bunch of random values. I mean, they're not really random, but you know what I mean, like some values into the vector. And then this will basically copy over the contents of V into R for array, right? So that's actually an STL function called copy. It is part of the algorithm library, so you #include algorithm. And so you basically give it the begin and end iterators, okay, to the container, which in this case is a vector. And then you give it the container in which you're going to store the copies of those elements, and that's going to be the simple array that we declared earlier. And then here's an example of doing it the other way around. Here you're giving it the container, right? But because this is a simple array, which doesn't have iterators, really what the dot begin would be in a simple array is just the name of the array, because that's just the starting base address of the array, right? And so the end address of the array is just going to be the base address, which is r plus n, right? So that is analogous to using the end iterator. And then where you're going to copy it to is going to be the starting base address of the vector v, which is just given by begin. Okay. Again, in line 12, we did not have to say r.begin, because number one, .begin is not available for r, but also because it's unneeded. R itself signifies the starting address of the container. Okay. And here's examples of using the sort algorithm. Both line 14 does it for an array, and line 15 will do it for a vector. Okay. And then line 16 is showing you an example of using the reverse iterators, which are r begin, r end, right? So basically, the code on line 16 would create another vector called reversed that will contain all the elements that were in v, but in reverse order. Okay. So that's about it. Any questions there? Let me see, I'll stare at okay, no questions there. All right, so here is another example using some syntax that was introduced in C++ 14, which was kind of a constructor-like syntax for iterators. So the differences from the between the previous slide and this one is basically lines 12 through 15, where you can see that it's using, instead of v.begin, right, is using begin, kind of looking like a constructor, and then you pass it v, the vector. And so this is, so I'm going to write it here, begin v is effectively the same thing as v.begin. That's just alternative syntax that was introduced in C++ 14. So it's really up to you which one you would want to use. They're both equivalent. I kind of like the previous one, or that's what I've used for most of my life, so I guess that's why I like it, because that's what was available before C++ 14. But this doesn't look that bad either. Okay? But it's a matter of style. All right, so type of iterators. This is particularly important slide for you, largely because sometimes if you looked at some of the sample exams, we do assume that you know the terminology for these iterators. Okay, specifically you have input iterators, output iterators, forward iterators, yada. Okay, so input iterators, you read values with forward movement. Conversely, an output iterator writes values with forward movement. Okay, and the important thing with either of these two is that there's no multiple passes, right? So you're going to do, you're going to be able to move the iterator through the elements. That you can do at your own pace by the usage of ++, but there's no going back. And in fact, once you reach the end of the container, that's it. Basically, at that point, the iterator is useless. Okay, so that's an input iterator, or conversely, output iterator in the writing case as opposed to reading. Now, forward iterator is a more flexible case. You can read or write values with forward movement. It can be incremented, compared, dereferenced, and store the iterator's value. So, I mean, basically, this is the iterator that you would want to use for most cases. And you can access the same value more than once. Okay, that's not. It doesn't include the restrictions that you had on the input and output iterators. Then an interesting one is the bidirectional iterator. This one would move back and forward. Forward and backwards, or back and forth. by way of the plus plus or minus minus, you do have to be careful when using this iterator, right? If you have some logic that is assumes that you're going to be moving the iterator forward, and then at some point your logic decides to move a step back, that can get quite tricky and it can introduce a lot of bugs, right? So sometimes, or I would say most times, you would want to stay away from a bidirectional iterator unless you have to, right? So if you have some specific logic that really requires, I mean, I can't even think of a situation that would require this, but if you have it, that you're searching forward and then you would search back and then forward, that's when you would use a bidirectional iterator. And then a random iterator is the same as a bidirectional iterator, but can also do pointer arithmetic, right? So you cannot do assuming that you have an iterator, right? A random iterator, you can do something like iterator plus equals 2. Okay, so that would mean that I'm going to jump 2. Okay, as opposed to plus plus. You're not necessarily able to use this code if you have a bidirectional iterator. So you'd always have to use plus plus, right? Now if that might not be right. I think you can use this syntax for the other iterators, but it would effectively take it as moving forward twice, right? You might not necessarily, and it's a linear number of steps that it'll take you to get there. A random iterator would basically allow you to do pointer arithmetic to jump, right? Kind of like random access, which is why it's called a random iterator. And that's the main point of the random iterator. And then a reverse iterator, which you actually already saw examples of in the previous slide, which is the R begin, R end. Those are reverse iterators. So it basically does exactly that. It iterates in reverse. Cool. Any questions? Let's see. Does auto in a range for loop use iterators behind the scenes? No, not necessarily. I believe it depends on the container itself on which you are calling the range, right? I think by default on range, every variable or every value that is taken on by the iterating variable is going to be a copy, okay? Unless you specifically tell it to pick up a reference rather than a copy. And then there I'm using pointer and reference analogous, right? Which, by the way, let me explain that. I don't know if anyone knows the difference between, let's see if anyone can respond in 30 seconds on the chat. Anybody know the difference between a reference and a pointer? Let's see, I'll give it 30 seconds. And Blake cannot answer. Difference between a pointer and a reference. And don't look it up. Well, I guess you can look it up. So. Let's see, reference doesn't know it's a reference. It thinks it's the original. Maybe there's some of that. Let's see, pointer knows it's a reference and can be changed to reference something else. Have reference as an alias, pointer is on its own. A pointer points. Ah, I see. A pointer points. That's pretty enlightening. To something else. Good to follow up with that very specific. All right, so it's actually quite simpler. The answer is a pointer can be null, right? So in other words, any reference is a pointer, but not the other way around, okay? because a pointer could be null, right? You can have a pointer that's not pointing, so it's not referencing something. Whereas a reference, it's always assume, which I think is what underrated one was trying to get at, right? If you're talking about a reference, it's assumed that there's an object that exists that has that reference, right? Whereas a pointer, you cannot assume that, because a pointer can point to nothing, to null. So it's basically the difference. This is why it depends on the context whether you can use the name pointer or reference interchangeably. Okay, because oftentimes they're the same thing, but you have that distinction. Okay, let's see. A pointer's value holds the address of the thing that it points to, and a reference is another name for a variable. Actually, that's not far off. It effectively is what I just mentioned. Cool. All right. So using iterators. So iterators really behind the scenes are pointers, which is why in the previous slides we were basically able to swap kind of the base address with the dot begin and stuff like that. They allow the implementation of the same algorithm for multiple data structures. The idea is if you're dealing with iterators, you don't have to assume anything about the container itself, right? That's the benefit of implementing algorithms that really deal with iterators rather than containers, right? If you were dealing with containers, you would have to make assumptions. If you're dealing with iterators, you don't, okay? Support the concept of sequential containers. Basically, that's all the iterator types that we discussed in the previous slide. Iterators help writing faster code for traversals. Kind of, but I would say this is, very minimal in terms of the benefit that you would get. This whole comparing of, taking an array and then dereferencing it, here, what you're doing is dereferencing the iterator itself, right? So you already have the iterator, you just dereference there, whereas, with R, you need R in order to be able to dereference R at that specific position, right? Which is what the, if you didn't know, that's what the square bracket does. It's a dereference of the array at the specific address that's given by R plus I. Okay. And so in the interest of time, there's some code there for the usage of iterators. I'll let you sort through that. Iterator ranges, we just saw examples of when in the previous slide when we were using sort and copy. That's your dot begin, dot end. I forget. C begin right here. That's for const. So it's a const iterator, right? So that was not in the previous slide, but you can have const iterators, which mean exactly that. It's an iterator, and furthermore, it's const, so you could not modify the iterator. You can increment it, but the object that is contained in the iterator cannot be modified. Const end, reverse begin, reverse end. This second bullet point is what we illustrated in the previous slide. What do you use with C arrays with these functions? Well, you use the array names themselves, and then you'll need the size of the array in order to be able to get to the end pointer, if you will. So STL operates on iterator ranges, not containers, is what I expressed earlier. Okay. So iterator ranges need not. That's a particularly important point. Iterator ranges need no random access, right? So that's what allows STL algorithms to potentially work for a container that has random access, but also for a container that does not have random access, right? Kind of also depends on the algorithm itself. But STL, since it takes on iterators, it'll just say, well, if your container is a list, then because I don't have random access, your runtime is going to be much worse. But if you give me iterators that point to a container that has random access, then the algorithm will run much faster, right? Linear time. So just a quick note, because we see this often in projects or in office hours, where folks try to create their own template function that would work for multiple types of containers. Try to, we'll stay away from that. If you try a function like, excuse me, like these two here on the slide. Excuse me, let me get a bit of water. If you try the code that's on the slide, it basically the compiler is going to get confused, right? Because this has to do with how containers are, the container inheritance in how they are created in the STL. So it will get confused. So what you would want to do instead is to create a function that should work for a specific container, right? Like the one that's on that slide. And then you'll have basically multiple versions of this function, one working for a list, for a deck. That's, and then you might be like, well, that's still kind of, I'm kind of redoing code for multiple types of containers. I would want to stay away from that. So the answer to that is, instead, your function here, instead of taking as input a container, should take on iterators, right? That's the whole point, right? Which is why STL in itself always relies on iterators and not the containers themselves. Okay. All right, memory allocation and initialization. Here's just a quick note on what you should keep in mind, especially as you go into projects and you pick which containers to use in particular situations. So, for example, a vector is one of the biggest advantages of a vector is that it's compact, right? Since it's really behind the scenes an array, right? Then it's an array. It's effectively a block of memory that's it's of size n, where n is the number of elements in the array, right? And it's all contiguous. It's reserved in memory in a contiguous fashion, which is different from a list, right? The list, every time you create a node that gets added to the list, it can exist in a different spot in memory, right? That's something to keep in mind. Of course, that's a disadvantage of a list, but then an advantage of the list is the fact that because you don't have to find a contiguous block of memory to create your array, upon creation, a list is very, very small, and then you don't have to worry about the size beforehand, right? The size of a list will grow dynamically as new nodes are added. Okay, whereas with an array, you have to always keep in mind what the capacity of the vector is versus its current size. Remember, size would be the number of elements versus the current capacity. And at some point, if you run out of capacity, then you kind of have to do something because you're going to run out of capacity. But with linked lists, there's no sense of capacity. There's no notion of capacity. Okay. An unordered map is a bit of a memory hog, and so are most hash tables. So keep that in mind whenever, especially for our projects, try to, there's points in which you will not be able to escape using an unordered map. So for example, an example of this, in project 1, you could have implemented your dictionary by using an unordered map because it's effectively a key value pair, right? Where the key is just an integer and the value was a word. So you could have said, okay, so this is an unordered map. And you would be right, but it would be a memory hog for something that could be much simpler, given the fact that you're keying off an integer, and you also don't care too much about what the actual value of the key is. So instead of using an unordered map, you can fall back to just a vector, which is acting like a map by having an integer key value. Okay. So keep in mind also, as you are creating, say, multi-dimensional vectors or arrays, right? So here is an example of 2 ways in which you can declare and initialize a 2-dimensional vector. They're both completely equivalent, right? There's no advantage of one version of the other than, I mean, no, actually there isn't. There is none. This is effectively the same thing as resize. Okay, so not much of a difference there. So it's up to you, style-wise, what you would want to use. Then there's this last example, which is particularly nice because the entire declaration and initialization is inlined, right? So this is multiple lines, same as this, but this is just one line. Okay, style-wise, that's up to you. Okay. Now, as you declare these multidimensional vectors, keep in mind that for each vector that gets created, there is an overhead, right? In fact, it uses 2 size ints. I mean, this is constant space, so generally we don't care too much about it. But nonetheless, it is overhead per vector creation. Okay. What that means is that when you declare multi-dimensional arrays or vectors specifically, you would want to actually have an ordering of the sizes for the dimensions in there. Okay, so here what I'm trying to get at is, let's say that our total overhead is just O, right? And let's say that for each vector has an overhead of, I don't know, 2 times O, whatever that is. So it's for every vector that you create, you're going to incur that overhead. There's another one. Here's another one, right? So and this is a multi-dimensional, like each one of these is a row, right? And then these are the elements in there. Okay. So what you would want to do is, so notice that there's overhead on the creation of each vector, but not on each element that it's on the vector, right? So basically, if you can arrange the dimensions of your multidimensional vector such that it is more rectangular, meaning the larger dimensions are used as the first dimension, right? So let's say that this is 10, right? And then I declare 3 of these, right? I'm not sure you can see that, but I need more space. This is better than creating 10 of the smaller sized vectors, right? So this would look more rectangular than if I use the dimensions in reverse order, right? So next time I'll try to see if I can come up with a better whiteboard than just writing on the slide. I have to technically see how to do that with this software, because not a lot of space on these slides. Okay, so basically this boils down to you'd want to, if you have larger dimensions, that's what you want to use as your first. So look at it this way: the largest dimension should be the first dimension in your multi-dimensional vector. Okay, so which is, so you reorder the dimensions to reduce the overhead. Cool. Any questions? What am I doing on time? I think we're doing good. Okay. Aren't maps relatively time efficient though? I read their access methods are login or something like that. Yes, I mean, they are, but again, the issue is in the context, if you can get away with just using a vector, you should. Because as compared to a vector, they consume a lot more memory. So, but there are situations in which you're going to need, in fact, as Blake mentioned, for later projects and later in the class, we're going to have examples where you can't use just a vector; you have to use a map. And when you do use them, they're quite efficient for what they are. Some utility functions. Again, you might have used some in project 1 even. Maybe swap is one that you might have been like, oh, that would have been useful to know for the. I do think we have it in the STL and U document, so should have looked it up there. But we do have a swap function, max. I already talked about those, and there are tons more utility functions. And as of C++ 11, we have what are known as Lambdas, which is just a fancy word for functors, if you recall from your 280 days. Functors is short for function objects. And then Lambdas is basically another name for functors. I mean, there is a slight difference, but we don't cover it here, and there's really no need to. So let's see first how functors work, and then we'll talk a little bit about the syntax of Lambdas, which as far as we're concerned, we call it syntactic sugar for functors, right? As you'll see with functors, you can end up having to write down a lot of code. And whereas with Lambdas, the syntax is, pretty compact. Of course, the bad side of that is that they're so compact, sometimes they're hard to, read. So let's say here's an example of using a functor. Suppose that you have a class employee that you want to sort. You could provide kind of like a default comparator by overloading the less than operator, because STL to sort, what's going to use is the less than operator, right? To compare the elements that are in the container, that's what it's going to use. So, oftentimes what we do is, there's some default way to compare your elements, so you might overload that. But if you do that, note that it's not going to be clear that if you want to provide another means of sorting the employees here in this example, then the fact that you have the default of less than, then it can be confusing for somebody that's using your employee class. Like, oh, am I supposed to use the less than always, or should I give it a comparator struct? So if you don't overload the operator less than, then it's easier for the person that's using your employee class to say like, oh, it doesn't overload the less than, so therefore I must provide a functor, right, to compare elements. And so that's the code that's on the slide right now. The sort by name is an example of a struct that is a functor, right? So sort by name, note that that is a class. It is a struct in which in there we would overload the open parentheses, close parentheses operator. Okay, and notice this syntax is particularly important. I would say 99% of the time would want to make this const, right? Because this is just comparing, so you should not be modifying, any elements as you compare them. If you do, actually, sometimes in our projects you can't get away from it, which not great software engineering, but there's only so much you can do with these projects. But in general, you really want to make these two parameters const, right? If you update the elements that you're comparing in a dynamic way, it can introduce a lot of bugs. Okay, and so all this is doing is basically comparing the names of the employees, right? So that's if you use this functor, in say a sorting function, then that's, it'll come out all sorted by name. Okay. Here's another example, which is, it looks involved, but it's not that bad. I suggest you copy paste this code and try it. It's quite interesting. It's basically, if you notice, index, the way it's initialized here is like all the elements are sorted, right? And then xchord has random values in it, given by that. And what this code does here, given that the sort by chord class, which is effectively a functor, takes on an entire vector, which you can have. And in fact, I don't recall what project 2 is going to be, but you might or might not end up having to do something like this. But the point is that this functor takes in, when you initialize it, a full vector of doubles. And so what this will do is then take your already sorted index and then scramble it based on the comparisons of the coordinates. Oh, sorry, I messed that up. So all bets are off as to what the output is going to be for the IDX vector. But notice that this is what it's doing, is basically taking the IDX vector, which is based on integers, and reshuffling based on double values that are contained in xchord. Okay? So it's an interesting bit of code for you to run just to see what it does and to just practice the usage of functors. There is also a utility function in the STL that allows you to fill up an array. So the example here, the function is called iota. It basically fills up the entire vector with the value 0 in this case, right? Pretty simple function to use and quite useful. So yeah, you could change this to be a 1 and it'll fill up the entire vector with the value 1. Okay. A note on randomization, because in later projects we will kind of use randomization. So it's good for you to start hearing how to use this. Also, you should be using this to basically test out your functions. So that's what it's useful for. You basically can use generators for generating random numbers, be it ints, unsigns, doubles. These are just all different algorithms for producing pseudo-random numbers, which is what any code will have to do, is generate pseudo-random numbers. Unless you're using a quantum computer, then it's not pseudo-random. But we don't have that. So they're all pseudo-randoms, and there's different algorithms for generating pseudo-random numbers. And then you can also generate distributions. We won't go as far in this course as to needing to generate distributions, but it's there for you. So for example, generating a uniform integer distribution. As you move on to other courses, keep that in mind, because you might use those, but really not in this course. I don't think we'll have a need to generate distributions rather than just a single random number. And note that using these generators are preferred than just using the rand, which you might have used before. For most purposes in this course, really you can get away with using rand, but note that there's other usages, other options for generating random numbers, like MT19937, which I don't know what really stands for. And then I know that the _64 stands for generating a random 64-bit number. Okay. So here's an example of generating random numbers. Again, this is great for testing a program, right? So if you, or testing a function even, right? So if you have a function that takes as input a vector of integers and it's supposed to do something, and you want to test it for really large vector sizes, then this is when it's useful, because you can generate
random values real easily. So, for example, this creates the vector. This is the code that we need to use the random number generator, which I guess is called mercenary twister. Okay. Anyway. And then iota, we use iota to fill all the values with zeros. And then another interesting utility function in the STL is shuffle, which will basically do exactly that. Shuffle the values in the values vector. Sorry for the name redundancy. According to this random number generator, which we just called G, very obscurely, which was declared in line 10. Okay, and then it prints out all those values. So that's for you to use and experiment with. Those are all example usages of functors in one way or another, right? So basically, this random number generator here is a functor, which is what we pass to the shuffle function. Lambdas are basically a much more compact, nicely written syntax, so syntactic sugar, if you will, for functors. They are a bit more than that, but again, not relevant to this course. For this course, they're basically just syntactic sugar. So it improves code readability by keeping code localized. There's no need to name a function elsewhere that you will only use once, right? So we'll see examples of that syntax in the next few slides, and then I'll stop it there in the interest of time. And then makes STL algorithms easier to use. Yes, easier to use, but not necessarily more readable. And then Lambdas, by the way, are all the rage in all sorts of languages. So if Java now has a Lambda library, Scala is basically a language that is built entirely on Lambdas because it's primarily a functional programming language. In fact, if you've done functional programming, you're very familiar with Lambdas. Just saying. So they're just like functors, so they can be passed around and used as function arguments. For example, callback functions. Callback functions is basically, just again another name for functor. So you're basically passing the function, and you're assuming that function is going to return at some point. And so when it returns, it's going to return within the context of or the scope in which it was passed. So Lambdas will not be in the exam. This is just, for your benefit. It's not something that we cover in exams, largely because it has this really cryptic syntax, okay? So instead of your usual syntax for creating a function, in fact, let's see if I can fit this here. Should make more space, right? But assuming that this returns a Boolean, right? Your function definition equivalent to this will be bool myfunc open int, and I'm sorry, this looks terrible. Try again. I'm just going to F for lack of space. Int n1 int n2. Oops. Well, looks something like this. Open parentheses and then the same body. Okay, so that's basically the equivalent function definition. Notice the differences. So we'll talk about that in a bit. So the thing that basically stays the same from kind of the normal way in which you create functions and the Lambda way is the parameter list, right? And that's actually quite important because it is what C++ is going to rely on to identify your function later on, the parameter list. And then the function body, that syntax is effectively the same, okay? What's quite new is the fact that you have no function name. In fact, lambdas are often anonymous. One of the things that you're trying to avoid is actually giving it a name, because you don't need to. If you have enough information from the body of the function, right, to determine what it does, then there might be no need to name it, right, because it's obvious. So if you're writing a lambda where your body is more than 5 lines of code, then that should not be a lambda, right? Lambdas are meant for small functions. So if it's too complicated, you should really extrapolate it into a formal function and give it a name. Okay. So so there it is. That's basically a lambda. The only thing that we haven't discussed is this capture clause notion, which we look at now. Well, not now, in the next slide, actually, because one thing we did not discuss, sorry, I forgot to mention the return type, right? There's also no return type in the syntax, right? So we're trying to remove the name of, or forget about the name of the function, and actually also forget about the return type, right? We're not explicitly telling what the return type is, because C++ should be able to figure it out by the return, right? It should look at the return and say like, oh, the outcome of this is a Boolean, so this is what I'm looking to return. So Lambdas will try to automatically deduce the return type of its function body, which is why a return type is typically not necessary. And again, another situation that arises is if you're, because in Lambdas you can explicitly state the return type with this syntax shown here. I would say if you're doing that, you might as well just extrapolate this into a function as well. But in case you still want to use a lambda and have a specific reason to state the return type, this is what it would look like. Okay. So now on with what the capture clause is, and I will finish it here just to make sure that we finish on time. The capture clause has to do with the scope of the function, right? So lambda is a function, right? There's no if or buts about it. It is a function, which means that it has a scope within it, and that it also lives within a particular scope. And in fact, if the lambda is created right here, for example, it means that the scope of this function lives within the scope of main. Okay. So the question arises: what do I do if I would want to reference some other variable? In this case, a container vect for it's a vector, which is in the same scope in which the lambda is created, right? So vect was created in the same scope as the lambda, and I want inside of the body of the lambda to be able to reference vec, right? By default, this is not possible unless you use the capture clause, okay, which is what it's used for, okay? And so here is a lambda example, and then if you wanted it seems that in this example, we changed it a bit. It's not using vec, it's actually using factor. But that's basically any of the objects or variables that are in the enclosing scope that you want to use inside of your lambda function. That's what's going to be listed in your capture clause, okay? And that's what's going to make it available to the syntax that sits inside of your lambda function, which in this case it's factor. My apologies, I thought it would have been vec, but it was actually this variable factor and not vec. But you could, depending on what the function would do, it could just as well be vec, right? All right, so in the interest of time, and let me see. Well, actually, I promise I'll only take a couple of minutes because I'm almost done. So the last thing I wanted to touch on, so that again, those are lambdas. I encourage you to look up a lot more about lambdas. It's not covered in the exam, so don't worry too much about it, but it's really interesting. Again, if you do yourself a favor if you understand Lambdas, because they are starting to be used heavily in a bunch of other languages. One thing about debugging STL errors, so when you compile, you might see a lot of errors that look like garbage, which are probably all errors related to the STL. And you might be, oh, STL is broken or whatever, but it's not really that STL is broken, is that you kind of broke STL, right? So if you get errors like these are induced errors, so they're due to the way that you're using STL. So make sure to double check function signatures and that you're using the STL functions and containers as they're meant to be used, which goes back to what we started this lecture with which is, make sure you have good use of the references for the STL, because, there's no hope for you to try to memorize everything. So that's a note on debugging, and then I'll finish with this performance comparisons of STL containers. Basically, this right here is filling an empty container with a bunch of different values. That's what this experiment is doing. And you can see that lists, not very good performance. Okay. Now, that kind of seems odd because asymptotically, this is the same, and you can see that asymptotically, it is the same performance as vector here, right? Asymptotically, there should be no, and there are no differences, again, asymptotically, but lists seem way, way worse than vectors. That's probably due to reference of locality. Again, it has to do with the issue that vectors are all contiguous blocks of memory. So things you can access faster than if all the elements are distributed across memory, right? And you have to jump from sections of memory to get at all the elements. Cool. So that's, the basically filling, again, an empty container with different values. Here's another comparison of fill the container with numbers from 0 to n and then shuffle random. You can see that, again, list is not a very good performer here. And again, this is probably due to the same reason. It looks a little bit like it would be quadratic, but I don't believe it is. I don't see how it would be quadratic, because search should just be linear time, just like it would be for vector. Well, yeah, no, actually that would make sense, but then vector is also, you can see it's bending a bit, so it's also quadratic, but just much faster, right? So again, asymptotically equivalent, but in practice, vectors are much, much faster. Fill the container with numbers from 0 to n, shuffle at random, pick a random position by linear search, right? So here is where kind of lists will shine, right? Because, one thing is, after you pick a position at random, you're going to insert 1,000 values at that position, right? So here, lists will shine because, at any position, it'll be able to insert right there with not much overhead. In a vector, you've already covered the notion of amortized time. So if you run out of, even though it's, O of 1 to insert into a vector, it is true that, oftentimes you will spend a good amount of time having to resize the vector, right? And so that's the penalty that you see here, and why the runtime of vector is not as good as list for this particular situation. And the blue line is DEC, which kind of always sits in the middle of things. It's actually very flexible and also can provide good performance in a lot of situations. Fill the container with numbers 0 to n, shuffle at random, pick a random position by linear search, remove 1,000 elements. This is basically the complement situation, so it's effectively almost the same thing, except that instead of inserting, we're removing. So performance is similar. And then lastly, insert new values at the front. And so notice that for that one, vector is really, really bad because now there is an asymptotic difference, right? This operation is effectively n squared for a vector, but linear for a list. Sorry, not even linear. Excuse me. Because in a vector needs to move all prior elements, but a list does not, right? I mean, yeah, a list, it doesn't look linear there, but it should be. But I think the difference is so big that it kind of looks like a constant value there. But yeah, so those are some interesting comparisons. We have the links there for you to look at in more detail. These comparisons, and online you can find tons and tons of these comparisons of STL containers. They are quite useful when you're kind of on the edge of what container to use for your particular situation, and oftentimes it is useful to consult these benchmarks of comparisons or comparisons between the containers to see what should work best. All right, so that's all for today. Sorry it went over time. We're trying to fix that to, this is why I'm not a day. And have a great day. Have a good night, and best of luck in Project 1. See you Thursday.